Okay, so I'll give you a few more moments to copy this. So we're doing a chemistry problem from section 3.2, chemistry example. Okay, um, that's correct, Michael, what you're saying, and we're going to get into that. Michael's talking about how the chemical reaction works, and indeed, that's important information. So in this problem, we have a compound C. It's formed when you combine two chemicals A and B. The resulting reaction between the two chemicals, A and B, is such that for every gram of A, for each gram of A, 4 grams of B is used. Okay, so for each, to produce this compound C, you have to combine 1 gram of A and 4 grams of B in that proportion in order to create the compound C. Now, suppose initially there are 50 grams of A and 32 grams of B, of those chemicals. Additionally, let's say it's observed after 10 minutes. Once the reaction begins, it's observed after 10 minutes that 30 grams of compound C is formed in 10 minutes. All right, so what we want to do is we want to let x of t be the amount of compound C formed after t minutes. We're going to find a differential equation for x of t, and then we're going to solve for the amount x of t. All right, and may I start showing the solution? Has everybody copied this okay? Okay, thank you, Kathia. Thank you, Andre. All right, all right. Hold on here. A moment. Okay, let's go to the next page. So we need to come up with the differential equation. Do you think that the rate of the reaction is going to be dependent on how much of chemical A there is and how much of chemical B there is? I mean, would that be, we have to have a starting point. Do you think, yeah, that's right, Michael. So the rate at which this reaction is going to occur, the rate at which compound C is forming, okay, like is dependent on how much of each of chemical A and B you have. Okay, that's called the law of mass reaction. And so if we go here to our solution, I first note that to make, for instance, 5 grams of compound C, we would need to have 1 gram of chemical A and 1 gram of chemical B, 4 grams of chemical B. We have to combine those A and B in that proportion, and that'll give us 5 grams of C. So therefore, I can sort of make the jump then that if I wanted X grams of C, I would have to use 1/5 X grams of A and 4/5 times x grams of B. Okay, so I go from something simple to something, you know, I mean, this is clear. And now that should be clear. Okay. All right, very good, Thomas. So now we have to set up the differential equation, and it is in a way intuitive how this would be set up. Because the rate of your reaction, the rate at which compound C is forming, should be proportional to the number of grams of A left as compound C is being produced, and the number of grams of B that are left as compound C is being produced. So the rate at which the rate of the reaction is proportional to the product of both of those factors. It's a lot like, remember the problem with like writing a differential equation for a virus spreading on campus. And the differential equation was proportional to the number of people who had the virus times the number of people who didn't have the virus. How many recall that problem from, like, I believe that was chapter 1, you saw that. Okay, Matthew, yes, thank you everyone, thank you. And this, it's the same kind of principle here. Now, naturally, you know, how many grams of A would be left as compound C is being produced? Well, we started off with 50. We have 50 grams of A. Okay, 50 grams of A, and you're gonna start using it. So if you subtract 1/5 x, 50 minus 1/5 x is the number of grams of A left as compound C is being produced. Okay, so like if x is 5, then you've used 5 grams, and so of A, so 45 grams of A are left. Similarly, for the number of grams left for B would be 32 minus 4/5 x. Are there any questions on that differential equation there? Let's see, Zachary is saying, would it be 49 grams left of A? Oh, I'm sorry, you're right. Thank you for correcting me, Zachary. If x were equal to 5, we would have 49 grams left of A, and we would have 28 grams left of B. That's right. Thank you. Now, I note here that we cannot make more than 40 grams of compound C. So there's a you know, I mean, you know, initially, let me ask you this. Initially, do you think the reaction's going to go faster in the beginning when we have a lot of material, a lot of A and B chemicals to make compound C? Do you think the reaction's going to go more quickly in the beginning? Or do you think the reaction will go more quickly at the end? Yeah, it'll be more in the beginning. So in the beginning it'll be quicker, because eventually you're going to run out of material and the reaction has to slow down. It has to slow down. Okay, and that's right. That's right. Good, Matthew, Zachary, and Thomas. So, but why can't we make more than 40 grams of C? Well, the reason is because the dx dt has to be greater than 0. And that makes sense because the amount of compound C, which is denoted by x, grows with time. Now, in the beginning, it grows fast. Later on, it'll slow down, but it's going to grow. So that means your derivative, dx dt, has to be positive. Well, if dx dt is positive, that means then that both of these factors here, this factor and this factor on the right, because we're assuming k is positive, okay. But I mean, well, yeah, I mean, let's say k is positive. But I mean, then both these factors have to be positive so that dx dt is positive. And so you can't go beyond 40 grams because once you hit 40 grams, the second factor is going to equal 0. And then dx dt is 0 and you've reached equilibrium. So basically we're assuming that, you know, the reaction is going to get slower. Theoretically, you never use all 40 grams of compound B. I got to be careful here. Theoretically, I want to say this right. Hold on. No, compound B, we had 32 grams, but I'm not saying this the right way. The point is that very simply, both factors have to be positive. And so the amount of X that is produced can't make it where one of the factors is 0, because the dx dt has to be greater than 0. That's the answer. Are there any questions on that? This is going to be important later on when we look at the graph of this x of t. Okay, may I go to the next page? All right, Matthew's good. Andrea's good, wonderful, and Thomas, good. Okay, so this differential equation is a little bit messy because you have these fractions in here, the 1/5 and the 4/5. Well, we can take care of that because, I mean, after all, this constant K1 is a constant, but we can adjust our differential equation. Look what we can do here. Here's the differential equation. What I can do is from the 50 minus 1/5 x, I can factor a 1/5 out and write that as 1/5 times 250 minus x. I mean, I can do that. We can do that. We know how to do math. Similarly, I can take 32 minus 4/5 x, and to get the fraction out of there, I can factor out a 4/5. So then I'll have 4/5 times 40 minus x. And then the 1/5 and the 4/5, I can bring them out in front. I can bring them out here, right? And then I can define a new constant k. My new constant k will equal k1 times 1/5 times 4/5. And then this is going to give us a nicer differential equation to work with. Keep in mind you have initial conditions. After 10 minutes, 30 grams of compound C is formed. Of course, in the beginning, at time 0, there's no compound C formed. The reaction hasn't started yet, so x of 0 equals 0. So they normally give you this initial condition, the second one, but then the first one you just have to use your common sense to know that, you know. I mean, it's basically common sense, but still, it's good to talk about it. It makes sense. It makes sense. Okay, so of course, we're going to have to separate the variables to solve this differential equation. keep this in order here. Okay, so now we're here, and how would we? Of course, the integral on the left side is the more difficult integral. How would we integrate that? What special procedure would we use? Okay, Zachary's referring to that.
The fractions, partial fractions.
That's right. Thomas, Ann, Michelle, and Michael and Zachary are all correct, partial fractions. And you would show this, right? So like these integration techniques, you always want to show them. Now, sometimes we use a MATLAB to help us, but this is something you could show. But in the interest of time, I didn't work this out. But I do have, like, you know, I do have the left-hand side rewritten, because I know you can do partial fractions. Okay, I know you can do that. But few people on the exam, incidentally, missed some partial credit on a problem or two because they didn't show the partial fraction work. And that's important. You know, I have to know that you understand your math, right? So, but at any rate, let's continue on here. May I go to the next page? Okay. Okay, let's go to the next page. Okay, so using partial fractions, I rewrite the left-hand side like this. And I do have it written out like in my notes. I just, in the interest of time, you know, I know that this step you can do. So you would, you know, this would be the A, and this would be the B. Yes, A is -1 over 210, and B is 1 over 210. Now that we've had this in here, I have to integrate the left side. Well, I'm going to factor out 1 over 210 from the left and write this integral of the sum as the sum of these two integrals. Okay. All right, and then of course, now we want to get our antiderivatives. One moment, keep copying. One moment. Hold on, let's put this over here. Okay, that's just my usual 5:30 p.m. telemarketing call. How many notice you get telemarketing calls maybe the same time every day? How many notice this?
Yeah, they kind of come in waves.
They come in waves. Okay, Justin. Yes, yes. I'm telling you. I don't know why. I mean, you know, well, I mean, you know, too many of these calls. All right, so, well, Andrea, I am happy for you. I wish Andrea has not seen one on a telemarketing call in a while. And now it's like robots. It's not even real people anymore. It's like robots, you know, recordings, crazy. All right, so let's continue here. So now I need to get the antiderivatives of these two integrals. And so the antiderivative of 1 over 250 minus x is going to be equal to negative log of 250 minus x. Now, oh, what happened to the absolute value? Well, keep in mind, since x is going to be less than 40, I want to be a little bit careful here about this. Where x is going to be less than 40, so yeah, that's right. That's actually correct. So that means these two factors are going to be positive for whatever x is. So we don't need to have the absolute value. Okay, and then what I'm going to do is I'm going to distribute that minus through the parentheses. And you're going to wind up with this. Okay. So the difference of the logs is the log of the quotient. And then I'm going to multiply both sides of this differential equation, I'm sorry, of that equation by 210. And that gets me right here. And then, of course, the right-hand side, well, I'm going to exponentiate both sides of the equation. And so I'm going to, in the end, for this part, I'm going to get 250 over x, 250 minus x divided by 40 minus x equals e to the 210 kt times C3. So this is a process you've done many times. Okay, now at this stage here, how many unknown constants are there?
Three.
Good. There are actually just two. The k is 1, and then e to the c2 power, and I appreciate all responses. Thomas, you see e to the c2 is c3, so here's my other unknown constant. Are you comfortable with that?
Yeah.
Okay, good. Is everybody comfortable with that?
Can you repeat that, please? Which ones are the unknown ones?
The unknown constants are the k here. So I'm looking right here at the last equation, the k,
Okay.
and then this e to the c2 power, which I write as c3. Okay, that being said, are there any questions before we go to the next page? All right. Thomas is comfortable. All right, well, let's move forward then. So, all right, we need to make use of two initial conditions. First one is that at time 0, before the reaction has started, there is no compound C formed. And then later on, we'll make use of the fact that after 10 minutes, 30 grams of compound C is formed. So this here is just a matter of using initial conditions, which I know you're very good at. I saw that on the exam. You had problems with initial conditions, and all right. So, I mean, I don't think I'm just going to let you copy this. All right, and I'll be one moment. All right, are there any questions on this page here? All right, if there are not, I will move forward. Okay, all right. Okay, very good, Andrea. All right, Thomas. And okay, good, good. All right, Christopher. So now we need to solve for this constant k. We'll have to take the log of both sides. And so I do that here. And k will be equal to 0.000599. So you have to carry enough decimals out to make WebAssign happy. You know, it likes accuracy. I think that's a good thing, not a bad thing. Okay, and then the 210 times the 0.000599 is equal to 0.1258. That's what that number is. That's 0.12, sorry, 0.1258. Okay, and now we're in a position now, after getting to here, we're in a position to solve for x, to actually solve for x. And I will do that on the next page. All right, is everybody good so far? May I move to the next page? All right. And incidentally, what we're doing here, we're doing example 2 from section 3.2. And I'm filling in some details into the solution for you. Chemistry problem is an extremely important problem. You know, how many learned the law of mass reaction in one of their other classes, one of their other chemistry classes? I think Michael T did. Well, I can't. I assume he by his comment in the chat, I assume he. Okay, Christopher has not yet. Okay. Well, intuitively it makes sense. All right, so no problem, no problem. All right, so now we got to solve this for x, and really it's just a little. It's algebra. It's a little messy, but it's no big deal. No big deal. Okay, so what I'm going to do is I'm going to let me see here. I'm going to distribute the 25/4 on the 40 and on the negative x. And if I do that, then I'm going to get 25x equals this expression on the right. 25 fourths times 40 gives you 250. That's how the 250 is here. And naturally, to solve for x, I want to get the x terms all on one side of the equation. So I'll add this x here. I'll add it over to the right side, and that'll get me here. And then I don't like fractions particularly in my answer. So the 25 fourths, well, to get that to not be a fraction, I'll multiply through both sides of the equation by 4. I'll multiply both sides of the equation by 4. And doing so will get me down to here. So on the right side now, on the right side here, I can factor the x out and then divide through by the 4 minus 25 e to the negative e to the 0.1258t. And this is going to give me a solution for x. And WebAssign should take this solution, but what they do is they write the solution. They like this factor here, this fraction here. They multiply the top and the bottom by -1, and then that'll get you this fraction down here. It just looks a little prettier, and it's a little easier to understand. So, like for instance, if you were to take the limit oh, hold on. Do I have an error? Hold on, Zachary. One moment. One moment. Okay, Zachary's making a comment here. Oh, okay. Hang on. No, I'm actually okay. I'm wrong about what I said. Hold on. What they're doing is they're multiplying. Let me phrase it the way I want to phrase it here. Okay. I wasn't right on what I said there. No, hold on. No, it's here. It's here. So here, if you multiply the top and the bottom by e to the negative 0.1258t. Okay, hold on. Multiply. There's a reason why they're doing it. I mean, WebAssign should take that answer, but there's a reason why they're writing it in this form. You're going to see, Antonio, why they do it. Hold on one moment. Okay, so if you distribute e to the negative 0.1, e to the power negative 0.1258t, you distribute it here, and you distribute it here. And similarly, this e to the negative point to the power negative 1, sorry, e to the negative 0.1258t, you distribute that here and here, then you will get this. You will get this. Zachary, does that make sense now? Does that help you feel comfortable? If you have e to the a times e to the negative a, what is e to the a times e to the negative a equal to? It equals e to the a minus a, right? Which is e to the 0, which is 1. Good. And so that's how you get this 1 here. Okay. And similarly, you get a 25 here. It cancels the exponentials out. And it turns out that when x of t is written this way, what would the limit of x of t be as t goes to infinity? I mean, you know, there must be some reason they wrote the solution in that pretty form. That's right, Michael. It goes to, well, it goes to 40. It goes to 40. I'll tell you what, let me go to the next page so you can see this. Okay, all right. People still writing a few things down. That's right. So if you take the limit of this, if you let t go to infinity, think in calculus 2 when you took limits of functions. Okay, you let t go to infinity. What's going to happen here? What's going to happen is this term here will approach 1 because that approaches, no, it approaches 0, right? Because you'll get e to the negative infinity, that approaches 0. And then this term here approaches 0 as well. So that's going to get you 1,000 times 1/25th that's left as t goes to infinity, and that's going to equal 40 then. And that's what we expect. We expect that as over time, as the A and B chemicals are used up, you'll get 40 grams of your compound. No problem. Yeah, Michael says T going to infinity means you're letting the reaction happen for a long time, and that's the max amount of C that's produced. That's exactly right. Paige, why does it flip but X doesn't? Well, on the left-hand side here, good question, Paige. On the left-hand side, all I did was multiply by a 1 on the left-hand side. X isn't affected at all. X is on the right-hand side. I'm just rewriting the left-hand side. Still equals X. Oh, for the last one? You mean here? You mean right here? Oh, okay. So what I did, all right, class. Okay, thank you. What I did here was I multiplied by -1 over -1 on the left side. And now you get this. Thank you, Paige. Thank you for asking that question. Okay, so let me go to the next page then if we're good. Okay, so that being said then, thank you. This is what X of t is. And this is a picture actually. This is from figure 3.2.4. This picture. It just shows you the, it's a graph of the solution. And you can see that the reaction is fast in the beginning, but then it levels off. And also clearly, as t goes to infinity, these terms die down to 0, leaving you with 1,000 times 1/25, which is 40 grams. And once you reach 40 grams, you're going to have, let's see here, you're going to have 42 grams of A, chemical A, and 0 grams of B. And that's what we would expect, because, you know, once you run out of chemical B, you can't produce any more compound C. This is a, I mean, how many think this is a really a beautiful problem? Yeah, very useful, very useful. Very interesting. Excellent, excellent. Thank you, Ann. Thank you, Matthew. Thank you, Thomas. Thank you, Michael. Yeah, very specific numbers. But, you know, it's nice to, I always try to, I just don't like, you know, like because I guess it's my training as a statistician, but I'm sure engineers have this training too. You know, I always like to see if my answers seem reasonable. You know, and the fact that the limit of this X of t is 40 grams makes perfect sense, because uh, um, once 40 grams of B are used, you're you know, it slows down. I mean, basically the reaction stops essentially. I want to say, I don't think I said that right. I didn't say that the right way. No. The key is the not how much compound C you have. Once 40 grams of C is formed, then that second factor is equal to 0, and that's the number of grams of B that are left. And if there's no more B, no more chemical B, the reaction has to stop. Of course, theoretically, it just kind of goes, it's very slow, you know, as you can see on the picture. All right, so let me know when you're ready, and we'll talk a little bit about then section 3.3. All right, let me stop the recording here.